We'll continue today the dynamic programming class. So I briefly went over these beginning slides. So I just touched on this, the very beginning. But what is dynamic programming? So that's a way to address a question that is so large that is overwhelming. We'll break it down into smaller subproblems. And the summation of the subproblems, the end of the solutions of the subproblems, is the solution for the big question. So that's, somebody called it dynamic programming, whoever came up with that approach. So we use that for alignment. So remember that alignment is something that we use to compare sequences. So when we are comparing that, you did this before. Remember when I taught you dot plots, you write some sequence here, and everybody they match, you put a dot there. And then you're like, oh, look, these guys, they form a diagonal. These guys, they form a diagonal. And that's why whoever was developing this dot plot said, I'm going to make a darker red for the matches that are more meaningful. Meaning, so this S matches this S, put a dot there. But this S also matches this S. And what was special about this, that is not special about this, is that this comes diagonally from here. Therefore, we say this S is a better match with this than with this. And then there are these guys who are like, they're not forming any pattern. So they, they're not either interrupting or being parallel. So these might be spurious matches. So not that meaningful. And okay, then again here, and the way, remember that you said before that the way to decrease the number of spurious matches would be to increase the word or window size. So, but for protein, the spurious matches they occur less often because protein has 20 different possibilities for amino acids. So each of these would be an amino acid, whereas DNA only has 4. So for DNA, normally the word size is larger to decrease the number of these random matches. So we are looking to keep that diagonal. So every time you find a diagonal, you're finding a string of characters that match between the two sequences we are comparing. And when we are doing dynamic programming, we want to keep that direction. So you will know what that means, but I will anticipate here. We are going to calculate a score for this match here. We're going to calculate a score for this match here. So each of these boxes is a subproblem. And when we look at this sequence and this is a sequence, our brains can very easily find which part is the extra part. But if these were much longer sequences or ATCs and Gs, it would be harder to find that. So in dynamic programming, we're going to keep a score for each of these. And you will see that as we move on a diagonal, the score tends to be higher. But sometimes moving horizontal would be a better match. Moving horizontal means that we are inserting an indel, or we're inserting a hyphen to indicate a gap. And moving vertically also means we are inserting a gap. It's just, the difference is if you're inserting a gap in this sequence or in this sequence here. So maybe you remember what that alignment looks like when it has the gaps. So those were hyphens. So if I'm aligning this with this, then my alignment would have gap hyphens to account for this extra portion on the this is a sequence. So this is extra in comparison to this. So my dot plot would look like that. The slope is different just because I threw this sequence in BLAST2, and in BLAST2 it writes this sequence, and then this is a sequence, so down up, and that's why this slope is different. So here, let's see what about dynamic programming. The dynamic programming is used so that we can construct the alignments in a short computational time. Because if you're going to do every single alignment possible, it takes so long that it's impossible. Let me give you an example. If you take the naive approach, which is I am just going to build every possible alignment, and I'm going to do a score, have a score for each alignment, and then I will look at every possible one and see which one is a better alignment. So I wrote here what I think are all the possible ones. I am aligning then and n, and I always try to use something short because the point is just to show you that there are many different possibilities. So in here, I have a mismatch between D and A mismatch between A and N, and then a match between N and N. So there would be like, if in BLAST2, there would be a vertical line here. So in this alignment, it accepted the mismatch, and then match. This other alignment here, it did better, right? Because instead of accepting a mismatch between D and A, it said, no, put a gap there, so the A gets shifted here, and now I have a match, and then this N is single, because okay, the string ended, so there's another indel here. So this alignment would have a better score than this, because we have two matches, while in this one we have only one. So the more matches you have, the better is your alignment. And the more matches you have without putting many of these guys, because every time we put a hyphen, we introduce a gap, there is a penalty for doing that. So the alignment that we do is a balance between accepting mismatches and adding gaps. And how do you know which one is better? That's why we do the matrix that you are going to do later. So here's one possibility, another possibility that is a really bad one. You're accepting a mismatch and you're introducing gaps and there is no match. This would be a very bad alignment. So the point of this figure here is to show you, imagine if just for a 3-letter by 3-letter alignment, if I was doing all the possible ones, how many possibilities I have. But if these words were longer, and if I did every possibility, how many does it take? So this guy, I'm guessing is a mathematician, and I'm guessing is a guy, but could be a woman. I should look that up. Calculated that if you had two sequences that are of DNA, right, because it's base pair, if you have two DNA sequences of 300 base pairs each, which is actually not that large, given that our genome is 3,200,000,000 nucleotides. So if you compare just 300 by 300, you end up with 10 to 88 possible alignments using the naive method, right? Do every one of them. And they say it's more than the number of particles in the universe. So you don't want a computer to do all of this 10 to 88 alignments, score all of them, and then see which one is better. That's why we use this thing that's called dynamic programming. So in an exam, when I ask you, why is dynamic programming useful? Then your answer is that it makes the number of comparisons possible, because it decreases the number of possibilities that we'll entertain. Okay, got it? So here you go. What is the dynamic programming? So, okay, an algorithm is a series of unambiguous decisions. So you tell the computer, if this, then do that. If not, do something else. The computer doesn't actually decide which one it likes better. If it has to invoke some sort of feeling that this not work for a computer. So that's why it has to be unambiguous. It's like one or the other. So the dynamic programming algorithm, and okay, already said what that means, is solving a big problem, breaking down into smaller problems, and then the overall answer is the combination of the smaller problems. I said this probably like 3 times by now, so that you know what that means. Kind of a big deal to be able to define dynamic programming. So the first people that came up with that were these guys that I said I don't know how to say this guy's name. And they developed this approach in 1970. And their idea was, this is how we score for global alignments. And then these two guys said, but I don't want to see just how two sequences overall resemble each other. Maybe I'm just looking, do they have any chunk in them that resemble each other? I want to do a local alignment. So what they did was they took the algorithms that these two authors developed, and they made some tweaking on the code to change the scoring so that the alignment that gets produced is a local alignment. You will see the difference between the scoring in like 2 slides. But the next one is just to remind you, what do the global and local alignments look like? So the global one is stretching the analogy, or stretching the alignment, and it tends to introduce more gaps in the middle and fewer in the ends, because it's trying to match the first and the last letters. The local one, we will put more gaps in the beginning and the end, and okay, sometimes in the middle, but it's trying to keep the letters together. So in the exam, I normally ask, and I told you this is an easy point question. You want to write it down. Maybe you want to keep like a little pad of all the questions that I already tell you I'm going to ask, the easy points ones. I ask you, what's the algorithm used for global alignment? And then your answer is Needleman, Wunsch, whatever. And then I ask you, what's the algorithm used for local alignments? And you say Smith-Waterman. Okay, so those are the names of the guys who developed them. And now you're asking me, okay, what did these guys do that then these guys modified to produce this different result? And I'll say, I'm glad you asked. So here it is. We are comparing this sequence against this sequence. And so here and here, and I'll tell you that the result of aligning this sequence would be down here. So there is an alignment that was made based on the traversing this matrix. And you're like, what does traversing the matrix mean? Traversing the matrix means that we are going to, for each of these guys, there will be a solution. We're going to do some calculation to come up with an answer here. We're going to compare F and F, and there will be a score here. Then you're going to compare F and T, there will be a score here. Then F and A, there will be a score here. So remember, we are having these are the partial solutions to the big problem. The big problem is, what's the score of this alignment versus, or this sequence aligned against this sequence. So we do the same thing over here, but put on the chat, what is the difference that you see that you don't know what it means yet? Well, I'll give you some hint on the yellow, but what's the difference between how this got generated versus this one? So let's see, this one, yeah, I agree with that. So Sydney says this one is global, this one is local. You were right. And like, people are like, how do you know that? Well, this kept all these letters together. So it's finding blocks of similarity. And then this block is smaller than that block. So we know that this one is for global. It tries to match from beginning to end. This one is local. It tries to keep letters together. And the way this gets accomplished is by What can you see? So good job, Sydney, comparing these. Now look at the scores. Like this scoring system came up with the global, and this scoring system came up with the local alignment. What is the difference between them? So I'm hoping that you look at the matrices. Or do you see that is different? It's not a trick question. I tell you when it's a trick question. Yay! Good, Alea, good, Tatiani. Yeah, so here, the one on the left has these negative numbers. The one on the right has all zeros. So you understand what those things mean, but these guys are called setting the initial conditions. So those are scores for the alignment as you traverse the matrix. We always start on this one. So no matter which type of alignment, and just so you know, when I make you do this on an exam or homework, I ask you to do this because it's easier. Because these numbers grow negative so quickly that it's easier to make a mistake with the Needleman-Wunsch than the Smith-Waterman. So you're going to do Smith-Waterman. And all I do is I give you this string, and then you grab some piece of paper and you put them on a matrix. You set the initial conditions to 0, and you go from there. That's the exercise we're going to do. But the point here is that this guy, there's only that one 0, which means that I'm going to compare the phenylalanine with this phenylalanine. And there will be a score here. And you're like, where's that score? The initial score, or the first score you're going to put here, is a score from the Blossom 62 matrix. If you remember, that's the amino acid substitution table that that couple, they compared a bunch of proteins, and then they said how often does one amino acid substitute for the other, and how likely are they to stay the same. So what I do is I look at the F and F on the Blossom 62 table, and I write the number kind of like on some little some corner here, because this is not just the final number yet. What I do then is I start on this corner and I move diagonally, and then there will be a number here. When I move diagonally, what I mean is there is a number here, and if I traversed, so if I went from here to here, I moved diagonally. If I went, for example, from here to here, I also moved diagonally, but I have to account whatever is the mismatch score here for T and F. I have to do -6 plus the mismatch score. So why do they vary by sizes? So the initial conditions on the Needleman-Waterman, they're all 0, and you will see later, because we don't want to penalize the alignment if the first letters don't align. So Tatiana asked me that, so I guess I can already address that. See these negative scores? That means if I don't align these first two to each other, that means that I'm putting in a gap, and then I'm losing points every time I put a gap. The losing points is the same here, but here the negative numbers amount more quickly. So this thing of setting the initial conditions to 0 is what Smith-Waterman did to produce a local alignment in contrast to a global alignment. All right, so in the exam, I ask, there are 2 modifications. I'm showing you one. What did Smith-Waterman do to produce local versus global? And one of the answers is they set the initial conditions to 0, while Needleman Wunsch don't. The negative numbers increase very rapidly. All right, so this is going to feel a little bit more real when I give you examples. But so far, so good. All right, thanks for answering, CD. All right, thanks, Caitlin. All right, so now we're like, okay, you already told us a little bit about it, but how does it actually work? So this is the game. For people that like doing little games, then you might enjoy this. If you're having trouble falling asleep, just grab this exercise and work on it in bed. That's the best way to fall asleep. So here's how we do it. And this is why we tell the computer to do it for us, because this is really boring. Why do I make you do this? Because I wanted to see that when the computer gives you some answer, it took some approach that somebody wrote the code for, and this is what the code does. All right, the first thing you do is to compare each of the letters and write the Blossom 62 score in some little corner. So I do that for all of them. So I will just give you an example here. F and F. So I go on this table and I go, okay, phenylalanine here, and I go like, oh, good. Okay, here's my phenylalanine, 6 points. So I write like a 6 on little in a corner here. It's not written in here yet. And then I do F and T. So F and, oh, where is T? Did I pass it? Here. So F and T -2. I write a little -2 in a little corner here. So do that for all of them. And so that first step is calculating the match or mismatch score. So match is when the two letters are the same. Mismatch is when they're not the same. So that comes from the substitution matrix, comes from here. So this is one matrix. Sometimes people confuse these two. This one matrix has these scores that we don't actually change. This came from empirical data. And these scores here are the ones we are calculating. This table here is the dynamic programming table. This here is the substitution table, substitution matrix. Okay, so I was telling you about moving, and this is how this works. You can either get to this point by coming from here, or from here. And we're just going to go in one direction. Like I go rows first, but we never go from here to there or from here up. We go from here to there and from here up when we are calculating the score of the alignment on something called traceback. But when you're traversing the table, which means we are calculating a score for each of these, we're just going to go from left to right and up down, right? So diagonal or across or down. And then you can see there are 3 calculations for each of these guys. So remember that we're doing the sub problems. So each of these solutions is the optimal solution of 3 different possibilities. So this is how you do it. You get the score from the cell that you're coming from, and then you add to the score of the Blossom 62 match or mismatch, and that's it if you're coming diagonally. So I had a 0, here's a 0, plus 6, that's the score of the match, that's 6. Great. Now, if I go this way or this way, I told you that I wanted to know this, that this means I'm introducing a gap. I'm putting a hyphen in my alignment. And that costs money. So it's basically like this. Should are F and F made for each other, they get some points. If F and F decide, no, I'm not going out with you, you passed a chance of being a good match, you lose some points, but maybe because you're going to get a better match later. So here you have a 0, and if you move horizontally, you're going to have that score that always starts as 0 in the Smith-Waterman, and then you're going to add the Blossom 62 score, that's that +6, but then you're going to subtract 6 points. The subtracting 6 points means that you open the gap. So if you moved horizontal or vertical, you are introducing a gap, and you're going to subtract 6 points when you open the gap. So here I'm telling you there are different paths. If you move down or across, when you move down or across for the first time, it's called gap opening. And in this one algorithm that I'm showing you, you lose 6 points. If you moved already once, and then on the next one, you move again once, there's a gap extension, and you lose only 1 point. So once you're opening a gap is a higher penalty. But continuing that same gap, you lose fewer points. So let me show you an example on the alignment. So for example, in here, or actually this one's a better one. In here, there was a penalty for opening a gap. But then this would be a gap extension. So the penalty for extending the gap is lower than the penalty of opening the gap. All right, so when you're doing this exercise, you go and put all the Blossom 62 scores, and then you add to the previous score, or you're going to add to the previous score here and here also, but when you move horizontal or vertical, you have to subtract 6. So when I ask you, what are the 2 modifications that Smith-Waterman did to the global alignment that Needleman and Wunsch came up with, you say 1, Smith-Waterman set initial conditions to 0. And the second thing is that every time a number here is negative, you round it to 0. So if a result is negative, you round it to 0. In the other one, they don't do that. So those are the 2 modifications that I want you to be aware of. And in the end, I'll show you a comparison so that you see. Okay, so I think this is when I want to give us a try at, yeah, so let me stop this part. And I want you to try to do that exercise